Good morning. Are there any questions? In the velocity, acceleration, and polar coordinates? Okay. All right, so for that question, we were told that r is equal to e to the a theta, and d theta dt is equal to 2. Okay, so if we find r dot, that's going to be a e to the a theta. R double dot is going to be a squared e to the a theta. And then keep in mind that theta dot is already given to us. That's 2, so theta double dot would be 0. Okay, so let me grab my notes real quick. All right, so if we take a look at this for vector v, we're going to have r dot times use of r plus r theta dot times use of theta. R dot, which is a e to the a theta, we're going to multiply that by use of r plus r times theta dot, so that's going to be 2 e to the a theta times use of theta. Okay. Any questions there? Yes, thank you. So that does make a difference. This is d theta dt on this, d theta dt on this. Okay, so let me, well, didn't mean to erase it all, but essentially. All right, so let's rewrite. R is equal to e to the a theta, and d theta dt was 2. So r dot should be a e to the a theta d theta dt, or we're going to end up with 2e to the a. So 2a e to the a theta. So r double dot would be 2a squared e to the a theta times d theta dt, or essentially 4a squared e to the a theta. All right, theta dot is 2, theta double dot is 0. All right, so the vector v, so it's going to be r dot use of r plus r times theta dot use of theta. So r dot would be 2a e to the a theta times use of r plus r times theta dot is going to be 2e a to the theta times use of theta. Okay, is that better? Any questions there? Okay, so now let's find A, the acceleration. So acceleration vector is going to be r double dot minus r times theta dot squared in the times use of r plus r theta double dot plus 2r dot theta dot in the use of theta. Okay, so r double dot we found to be 4 so 4a squared e to the a theta minus r, which is and theta theta dot squared is going to give us 4. Then we're going to have that times e to the a theta, and that's in use of r, plus r times theta dot. So this is essentially going to be 0. And then we're going to have 2 times r dot theta dot. So 2 times 2 is 4 times, oops, wrong way. 4 times this, which is going to give us 8 a e to the a theta use of theta. Okay, so this is what it should end up with. All right, any other questions?
For this question on the answer sheet, it was like simplified. Do we have to simplify, or we could just leave it as this?
If let me see what I did. You don't have to factor that out. I mean, you can, but you don't necessarily have to. And let me check something. Because if I simplify this, I'm not going to get what I have typed. Or I didn't screw up something. Double check and make sure I didn't type the answer in wrong. Did everyone get 4 for this, not 8?
I think the answer you got here is correct.
Okay, so I'll fix it on the thing so it can match. Okay, so now it should match up correctly. All right. Any other questions? Okay, so what we're going to do is continue our section dealing with functions of multiple variables. We are ready for our next example dealing with the last example dealing with sketch the levels, the typical level surface of a function. Okay. So for that one, this is part C of that, we have that f of x, y, z is equal to y squared plus z squared. Okay. So if we take a look at this, all right. So if we take a look at this, what variable is voided of in this function? So it's x. So that means that x can take on any value. So we know that this is going to go along the x-axis. Now, if we take a look at this, as far as this is concerned, if this was equal to a this expression here is equal to a number, we're working with a what? We're working with a circle. So what we're going to do is to set this equal to an easy one of 0. Okay. So basically, I mean, not 0, 1. So if we do this, that means we're going to have a circle in the YZ plane. So we're going to have centered at 0, 0. Then we're going to have the circle in the YZ plane, which is going to look like this. Now, this circle is going to be, you're going to be able to basically carry it along in both directions parallel to the x-axis. And basically, you're just going to have circles going in so, like so. Okay. And this will be the typical level surface for this. Any questions? Okay. All right, let's look at the next example. So the next example is going to be similar to what we did in the previous one with the level curves, but we're going to do it with the level surface. So we're going to find an equation for a level surface of a function through the given point. So for the first one, we are given that the function is f of x, y, z, and this is equal to the natural log of x squared plus, let's see here, plus y squared plus z squared. Okay, and the point that we're given is negative 1, 2, 1. All right, so essentially what we're going to do is to evaluate the function at negative 1, 2, 1. So if we do that, we're going to have this. We're going to have the natural log of 1 plus 4 plus 1, or we're going to end up with the natural log of 5. Okay, so this is what we're going to set the function equal to. So we're going to have the natural log of x squared plus y squared plus z squared, and this is equal to the natural log of 5.
I think it's natural log of 6, right?
It is. Miscount it. There we go. Okay. So really, this is the same thing. If we simplify this, it's the same thing as saying what? what would this simplify down to?
A squared plus z, 1 squared plus z squared is 6.
And this is equal to 6. Okay. And if you think about this, this represents the equation of a what?
Sphere.
Yes, it represents an equation of a sphere. Okay. Any questions? Okay, so next, let's look at the next example. Okay, so in the next example, we have g of xyz is defined as the integral from x to y of d theta over the square root of 1 minus theta squared plus the integral from square root of 2 to z of dt over t times the square root of t squared minus 1. And we're given a point of 0, 1/2, and 2. Okay. All right, so the first thing we have to do in order to do this problem is we actually need to find out what the function is. Okay, so what we're going to do is we're going to have that g of x, y, z is equal to, all right, so we're going to start off with this portion here. If we integrate that, what does it integrate to?
Sine inverse.
Okay, so we're going to have the sine inverse of theta, and we're going to evaluate it from x to y. Then we're going to have plus. Now we need to integrate the second piece. What does the second piece integrate to?
Secant inverse, right?
Okay, so we're going to have the secant inverse of t, and we're going to evaluate it from the square root of 2 to z. Okay, any questions there? So essentially what we're going to end up with is we're going to have the sine inverse of y minus the sine inverse of x plus the secant inverse of z minus the secant inverse of the square root of 2. Okay, so basically our function g of x, y, z is defined as this. So sine inverse of y minus the sine inverse of x plus secant inverse of z minus. Now, the last piece was the secant inverse of pi over 2. Well, what is the secant inverse of pi over 2? I mean, excuse me, secant inverse of just square root of 2. Excuse me. What is the secant inverse of square root of 2?
Pi over 4.
Right. We're going to put pi over 4 there. Okay. So now what we're going to do is evaluate this function at the point which is 0, 1/2, 2. Okay. So if we do that, we're going to have the sine inverse of 1/2 minus the sine inverse of 0 plus the secant inverse of 2 minus pi over 4. Okay, so what is the sine inverse of 1/2?
Pi over 6.
Okay, minus the sine inverse of 0
0.
plus what's the secant inverse of 2 so what's the secant inverse of 2?
Is that pi over 3?
Right. Okay. And then we've got minus pi over 4. Okay. All right. So if we simplify this, what does it simplify down to? Yes, it does simplify down to pi over 4. Good. Okay. All right. So basically what we're going to do, we're going to put this in place of g of x, y, z. So we're going to have that sine inverse of y minus the sine inverse of x plus secant inverse of z minus pi over 4 is equal to pi over 4. Or basically, if we clean it up, we have that the sine inverse of y minus the sine inverse of x plus the secant inverse of z is equal to what?
Pi over 2.
Yes, is equal to pi over 2. And that will represent our equation. Okay. Any questions? All right, so are there any questions over dealing with functions of multiple variables? Okay, so next, what we're going to do is to move into dealing with limits. In continuity in higher dimensions. Okay, so if you, and instead of me just trying to read this out loud, give me a second, and I'll post that up here real quick. Okay, so taking a look at this, so if we take a look at this, first we have a definition. So we can say that a function f of xy approaches the limit L as xy approaches x of 0, y sub 0, and write it as the limit as xy approaches x of 0, y sub 0 of f of xy is equal to L. If for every number epsilon greater than 0, there exists a corresponding delta greater than 0 such that for all x, y's in the domain of f, absolute value of f of xy minus L is less than epsilon whenever 0 is less than the square root of x minus x of 0 quantity squared plus y minus y of 0 quantity squared is less than delta. Okay, so this here basically is just referring to just the limit definition. Okay, the limit properties, I will post those up for you. I'll create a page and post those properties for you. But it's kind of the same properties that we already have for limits when we were dealing with one variable, so they're not differing a great deal. Okay, but I will create a page for that and post that. All right. Definitions, another definition, a function f of xy is continuous at a point x of 0, y of 0 if. Okay, so this is kind of the definition of for being continuous. If f is defined at x of 0, y of 0, the limit as x approaches the limit as xy approaches x of 0, y of 0 of f of x exists, and that the limit of xy as approaches x of 0, y of 0 of f of xy is equal to f of x 0, y of 0. So if you think about this, was the same definition that we used in one dimension when we were dealing with checking for pointwise continuity. So basically, this is the definition of checking to see if a function is continuous at a point. Okay. So this is basically what that definition will look like when you start dealing with multiple variables. All right. Next, two-path tests for non-existence of limits. It says if a function f of xy has different limits along two different paths in the domain of f as xy approaches x of 0, y of 0, then we say that the limit as xy approaches x of 0, y of 0 of f of xy does not exist. Now, this we're going to do a couple of examples to show you how to create these two different paths so that you can show that a limit does not exist. All right. Next is dealing with continuity of compositions. So it kind of works the same way as it does with when it was one variable. So if each function is continuous, then their composition will be continuous. Okay, so if function f is continuous over all real numbers, function g is continuous over all real numbers, then the composition of f and g will be its domain will also be all real numbers. So that's not really changing much. Okay, any questions? All right, so now let's move to taking a look at examples. So let me change back screens. Okay, so if I want to take a look at examples, all right, so the first example, we're asked to evaluate the limit. And the problem says that we're looking at the limit as xy approaches to -3 of the function 1 over x plus 1 over y quantity squared. Okay, so if we take a look at this, and basically in order to evaluate a limit, if we remember from calc 1, you basically are going to go with direct substitution. So essentially what we're going to do is direct substitution. So if we do that, we're going to have that 1/2 minus 1/3 quantity squared, and that's equal to, well, if we simplify 1/2 minus 1/3, what do we get? We get 1/6, and we're going to square that, so we get 1 over 36. and that will be our limit. Any questions? Okay, all right, next example. We have this. We have the limit as x, not x, it's y, approaches 1 of cosine of the cube root of the absolute value of xy minus 1. Okay. So again, in order for us to evaluate that, we're just going to do direct substitution. So we're going to have cosine of the cube root of, if we plug in xy, I mean both x and y here, what are we going to get?
1.
Okay, so we're going to have the absolute value of 1 minus 1. Well, really, that's going to be the cosine of the cube root of what?
0.
Okay, and what's the cosine of the cube root of 0?
1.
It's going to be pi over 2.
Oh, yeah. 2.
Okay. Oh, excuse me, it's not going to be pi over 2. I missed. No, it's not pi over 2. It is 1. Not sure why I was thinking it's pi over 2. I was thinking his inverse trig. So it is equal to 1. Now, if it was cosine inverse, then it would be pi over 2. Okay. All right. Any questions? Okay. So the next one, we have this. We have the limit as xy approaches 1, and we're told that x is not equal to y. And then we have x squared minus y squared over x minus y. Okay. So if we take a look at this, if we do direct substitution, okay, we're going to end up with 0 or 0, okay, which is an indeterminate form. So basically it tells us that by the means that we're trying, the limit does exist, but not by the means that we're trying. So we got to try something else. So if we look at this, okay, one of our biggest tricks that we used when we were doing limits was basically being able to see if it factors. So if it factors, the numerator does factor nicely into x minus y times x plus y. And that's going to be over x minus y. So we are able to remove that term that is causing issues. Now, when we do the direct substitution at this time, we're going to end up with a value of what?
2.
We end up with a value of 2. And that would be the limit. Okay. Any questions? Okay. All right, next example. We have this. So we're looking at the limit as xy approaches 2. And we know that x plus y cannot equal 4. And we have that x plus y minus 4 over the square root of x plus y minus 2. Okay? And again, as I stated, if we do direct substitution, basically we end up with 0, 0, okay, which is an indeterminate form. So on this, you can do this problem one or two ways. One way you can do it is that you can factor. Another way of doing it, you can rationalize the denominator. Okay, I'm going to go the lazy way and just factor. And it's basically the numerator that it does need to be factored. So we're going to end up with the limit as xy approaches to 2. And again, x plus y is not equal to 4. So the numerator factors nicely, and it factors into the square root of x plus y minus 2 and the square root of x plus y plus 2. And then this is going to be over the square root of x plus y minus 2. So once we get it here, we realize, okay, we can get rid of the square root of x plus y minus 2. And now when we do the limit, we're going to end up with an answer of what?
Four.
Yes, we end up with a limit of 4. Any questions? Okay. All right, next example. All right, so this time we have the limit as p approaches 1, negative 1, negative 1 of 2xy plus yz over x squared plus z squared. Okay, so p is just standing, instead of writing out x comma y comma z, p is standing for that. Okay, so again, with this, what we're going to do is direct substitution. So if we plug in, we're going to have 2 times 1 times negative 1 plus negative 1 times negative 1 over 1 squared plus negative 1 squared. So if we clean it up, for the numerator, what does that simplify down to?
Negative 1. Yeah, just 1. Oh,
Is
no,
it
negative
1?
1.
Okay, it's negative 1. All right, and the denominator simplifies down to what?
2.
So we end up with negative 1/2. Any questions? Okay, so if we have this, the limit as p approaches 0, negative 2, 0 of the natural log of the square root of x squared plus y squared plus z squared. Okay, all right, so you find out what that limit would be. So what would that limit be equal to?
Natural log of 2.
Yes, that's going to be the natural log of 2, because when you plug in, you're going to end up with the natural log of 0 plus 4, square root of 0 plus 4 plus 0, or the natural log of the square root of 4, which is the natural log of 2. Okay. Any questions? All right, so next, Okay, so the next big thing that we have that we do is, and if you remember from limits, one of the other big thing was dealing with continuity. Now, with continuity, again, it's just a fancy way of saying, okay, state the domain for the function. All right. So the next part example we're going to take a look at is what at what points x and y in the plane is the function continuous. So our first one, we have that f of xy is equal to x plus y over x minus y. Okay, so if we want to do the domain of this function, okay, now just keep in mind that with this is a rational function. So it's basically the denominator that we have, we need to make sure is never zero. So for this, we could say that the domain would be all points x, y, except, so what would be our exception? Yeah, so when our exception is when x is equal to y. Okay, so our exception is x is equal to y. So all points x and y work except for when x equals y. Any questions? Okay. B, we have that f of xy is equal to y over x squared plus 1. So what would the domain of this be?
All points x and y.
Right. So all points x, y. Okay. There's no exceptions here because keep in mind there's no y in the denominator, so y is going to make it. It's not going to make it undefined. Also, since x is being squared and you're adding 1, the number is always going to be positive. It's never going to be ever negative. Okay, so since it never can be negative, that means it never will cross. It never becomes 0. Okay, it never will become 0. So there's no way for this to ever not exist. Any questions? Okay, let's look at C. We've got f of xy is equal to 1 over x squared minus y. So what would the domain be?
All points x and y except x squared equal to y, right?
Okay, so all points xy except when?
X squared equal to y.
Okay, yeah. So y equals x squared or x squared equals to y, same thing. Okay. Any questions? Okay. All right. So now what we're going to do is to just move up and so we're going to move out of a plane and we're going to move into space. We're still trying to find all the points that make it continuous. All right. So next example, our function is defined as f of x, y, z, and this is equal to the natural log of x, y, z. We want to know what the domain would be. So what would the domain of this be?
All points x, y, z except x, y, z cannot be 0 or less than 0.
Correct. Okay. So we can say all that. So all points x, y, z except x cannot be less than or equal to 0, y cannot be less than or equal to 0, z cannot be basically less than or equal to 0. Or we can just simply say that it's all points x, y, and z where x, y, and z are greater than 0. Okay, so you can kind of say it either way. Okay, so all points x, y, and z except for x less than or equal to 0, y is less than 0, z is less than 0. Or you can simply say that all points x, y, and z where x, y, and z are all greater than 0. Okay. Any questions? Next, we have this. We have f of x, y, z is equal to e to the x plus y times the cosine of z. So what would be the domain of this function? So let's think about this. All right. Are there any values of x and y that would make e to the x plus y undefined? No. Are there any values of z that make the cosine of z undefined?
Yes.
What value or values? So let's think about the cosine function. Okay. There are any values that will make the cosine function undefined? So are there any values that will make the cosine function undefined? No. Okay. So we already said that there was no issue with the e portion. There's no issue with the cosine portion. So basically, it would be all points x, y, and z. Yeah, so like the cosine inverse, we do have restrictions, but for just regular cosine, there are no restrictions. Any questions? So, last problem, we have this. We have f of x, y, z is equal to 1 over absolute value of xy plus absolute value of z. So, for this, what would the domain be?
All points x, y, z except like everything is 0.
Everything in 0 is a would be just one possibility. So it is going to be all points. X, Y, Z, except, okay? So basically to represent this, all right, you are going to have 2 points that are always, that you're going to be looking at, okay? So for this piece, we always are going to make that 0, okay? Now for this piece, does both x and y have to be 0 at the same time?
No.
No. So I can do one point that's represented like this, and I get a point represented like this. Okay? And if the points are in this format, that will make this whole denominator 0. So we can't simply just say that x, y, and z are 0 because that only identifies only one point. But there are more than just one point. Okay? There are infinite number sets of points, but they've got to be written a certain way. Any questions?
Yeah, makes sense. Can we add 0, 0, 0 as well? No.
Well, 0, 0, 0 is included.
Okay, I see.
Okay, so it's an automatically included point already in this. Okay, so but 0, 0, 0 is just one of the many solutions that could happen. Okay, any other questions? Okay. All right. So we have one more part for this section that we are going that we're going to be finishing up here in a moment. So before we start into that, what we're going to do is to take a 10-minute break, and then when we come back, we'll finish up the last piece, which is dealing with basically the two-part, two-path approach to determine if a limit does not exist. Okay. All right, so we'll reconvene at 12:05. All right, so let's finish up our last little bit here. Okay, so in the last set of problems, what we're going to be doing, we're going to be considering different paths of approach and show that the function has no limit as x approaches 0, 0, xy approaches 0, 0. So first example we have is this. We're going to have that f of x, y is equal to x to the fourth over x to the fourth plus y squared. Okay, so in order to help us with this, what we're going to do is our goal is to rewrite this function in terms of one variable. Okay, so what I'm going to do is I'm going to let y equal to kx squared. Okay, and k is just some additional constant that's going to come into play. Okay, so what I'm going to do is to rewrite this and look at it in terms of a limit. So it's going to be the limit as xy approaches 0, 0. Okay, and we're going to go along this curve, this y equals kx squared, okay, of the function x to the fourth over x to the fourth plus y squared. Okay, so what we're going to do now is to plug this in. So we're going to get rid of y. We're going to plug in this expression for y and get rid of y so we have everything in terms of x. So we're going to have the limit as xy approaches 0, 0. And what we're going to have is we're going to have x to the fourth over x to the fourth plus. Now, if I put this in place of y and squared, it's going to give me k squared x to the fourth. So now what I can do, since I've got this down to one variable, I can look at this as the limit as x approaches 0 of x to the fourth over, in the denominator here, I can factor out an x to the fourth. And I'm left with 1 plus k squared. And when I take the limit of this, these cancel. So I'm going to get 1 over 1 plus k squared. Okay, so this is this is the limit that I get. Okay, so what I'm going to do is I'm going to choose some different values for k. Okay, so the first time what I'm going to do is say, well, suppose that k is 0. Okay, so if k is 0, I'm going to get 1 over 1 plus 0 squared, and I get 1. But what happens if I choose a different value for k? Suppose k is 1. I'm going to get 1 over 1 plus 1 squared, or I'm going to get 1 half. Okay, so essentially what I've done is I've gone through the process and I've shown what the limit would be in terms of one variable. And then what I've done for this is chose two different paths and show that I don't get the same limit, because you have to remember, in order for a limit to exist, it must approach the same value. So I'm showing that when I choose two different paths, I don't get the same limit. I get a different limit. So this is how you show that this is not that this limit does not exist. Okay. Any questions? Okay, let's look at the next problem. All right, so for the next one, we have this. We have f of xy is equal to xy over the absolute value of xy. Okay, so the first thing we're going to do is we're going to look at this and we're going to let y be equal to. Now, keep in mind that we want to make sure that we choose it in such a way that we're going to be able to get rid of x. So what do you think y should be equal to? So what do you think y could be equal to? I don't want to use 1 over x because I want to leave the x in.
Just x.
I don't want it to be just x. Okay, so if you think about it in the previous example, I introduced a constant, correct? So yes, I want it to be kx. Okay, I want it to be kx. So if I take a look at this, basically what I'm going to do is I'm going to take the limit as xy approaches 0, 0, and we're going to go along y equals kx. Okay, so of xy over absolute value of xy. So what we're going to do is to put in, replace y with kx. So I'm going to have x times kx over absolute value of x times kx. Okay, so now, since I've got everything down to one variable, I can say this is the same thing as in the limit as x approaches 0 of ax squared over absolute value of kx squared. So really, the same thing as saying the limit as x approaches 0. Okay. Now, the numerator, there's nothing I can do with that. All right. Now, for the denominator, I can rewrite that. Okay. And keep in mind what I can do, since it's absolute value, I can split it up. So I can do the absolute value of k, and I can do the absolute value of x squared. But let's think about this. What does absolute value do all the time? What does an absolute value do to a number?
Basically get rid of the negative sign, right?
Right, it makes it positive. But if I do the absolute value of x squared, really that's just what?
Just a squared, right?
Right, because you have to think about it. If I take a number and square it, it always makes it positive. So if I'm trying to take the absolute value, I'm trying to make something positive that's already positive. So I can get rid of the absolute value. Okay. So what happens here is once I get here, I realize that, oh, okay, I can get rid of that. So what the limit is equal to is going to be k over the absolute value of k. Okay. So if I'm looking at this to be what this limit is going to be equal to, so what I'm going to do is to pick values. So suppose k is 1. I'm going to get 1 over absolute value of 1, which is going to give me what? It's going to give me 1. Okay. Now I'm going to choose a different path and see if I get the same limit. So suppose that k is equal to negative 1. So I'm going to have negative 1 over the absolute value of negative 1. And that's going to give me a value of what?
Negative 1.
Negative 1. So I've shown that I've chose 2 different paths and I get 2 different limits. Okay. Any questions? So next. All right, so next one, suppose that we have this. We have function f of x, y, is equal to x squared over x squared minus y. Okay, so I want to show two paths. All right, two different paths. So what do you think I should let y be equal to? So what do you think I should let y be equal to?
KA squared.
Okay, so kx squared. All right. So what I want you to do is to take a couple of minutes and go through, find out what the simplified limit would be, and then run your two tests, your two paths, two different paths, and see what your limits come out to be. Okay. So did you end up with this expression? Good. So now all you got to do is just test. So suppose k is, let's suppose that k is 2. So if k is 2, I'm going to get 1 over -1 or -1. And then suppose that k is, I'll choose -2. I'm going to get 1 over 3. So I get 1/3. So I've chose two different paths, and I've got two different limits. Okay. Any questions? Okay. So what we're going to do is take a look at the last two examples. Okay, in the last two examples, sometimes just simply saying that let y be equal to something won't work. So sometimes you have to switch to a different coordinate system in order to help you out. Okay, so let's remind everyone about things. Let's remember that x is equal to r cosine of theta, y is equal to r sine of theta, and that x squared plus y squared equals r squared. Okay, and these are dealing with polar coordinates. So this is what we're going to use in order to help us out with these last two problems. So the first problem, we have this. We have f of x y is equal to 2x over x squared plus x plus y squared. Okay. So what I'm going to do is to switch this over to a function in terms of r theta. Okay. I'm going to switch this over to a function in terms of r theta. All right, so in place of x, I'm going to put in this. I'm going to have 2r cosine of theta over. Then next, for the denominator, this plus this we know is equal to r squared. So that I'm going to replace with r squared plus, then I've got this lonely x by itself, so but I know it's equal to this. Okay. So this is what this function looks like converted over in terms of polar coordinates. Any questions? Okay, so if I take a look at this, kind of my issue here is that I've got the cosine theta in here. Okay, so what I'm going to do in this case, I'm going to let r equal k times cosine of theta. Okay, so what I'm going to do with that is I'm going to rewrite this function and get rid of the r's. Okay, so basically what I'm going to have is going to be this. I'm going to have 2 times k cosine of theta times cosine of theta over k cosine of theta squared plus k cosine of theta times cosine of theta. So essentially I'm going to have 2k cosine squared theta over k squared cosine squared theta plus k cosine squared theta. Well, if I look, what it's going to cancel out is basically going to cancel out.
Cosine squared theta.
Yeah, so the cosine squared theta is going to cancel out. So I'm going to be left with 2k over k squared plus k. Okay. Now, I know when I get here, I can cancel out a k also. So I can get 2 over k plus 1. Okay. So this is what this expression would simplify down to. Now, if I take a look at this and do the limit, and again, I can pick values for k to get my two different paths. So if I let k be 0, I'm going to get a value of what?
2.
and a value of 2. And then if I let k be 1, I'm going to get a value of what?
1.
1. So I've shown 2 different paths, and I get 2 different limits. Okay. Any questions? Okay, so let's look at one more. All right, so the last problem we have is this. We have f of xy is equal to x squared minus y squared over x squared plus y squared. All right. So again, what I'm going to do is to transform this function over to a function instead of x and y to r and theta. Okay, so in place of x, I could put in what?
R cosine theta.
Okay.
Square.
So I can have, it's going to be r squared cosine squared theta minus, in place of y, I can put in what?
Sine squared theta.
Not quite just sine squared theta.
Yeah, just R squared sine squared theta.
Okay, so it's going to be r squared sine squared theta. And then for the denominator, what can I replace that with?
R squared.
Okay. Now, essentially, if I look at this basically simplifies down to just what?
Cosine squared minus sine squared theta. Minus.
And really, this is the same thing as saying dealing with what? So what is cosine squared theta minus sine squared theta? Yeah, it's cosine 2 theta. Okay, so this is what this simplifies down to. Well, let's think about this. All right, so cosine of 2 theta. All right, so let's think about cosine. Cosine is bounded between what and what? So the y value for cosine is bounded between what and what? -1 and 1. So -1 on the lower end and 1 on the upper end. Okay, so let's think about this. All right, we're trying to say that when we do the limit of this as it approaches 0, 0, we're basically going to get an answer somewhere. If we choose two different paths, we're going to get an answer somewhere between -1 and 1. Okay, it's never just -1, it's never just 1. Okay, so since I have an infinite number of values that it can take on between this, we don't have to go through the process of doing the k and everything, because this right here basically tells us that when I choose my theta, okay, I can choose 2 thetas and be on 2 different paths right off the bat, right off the jump. Okay, it's not coming down to one single value. I've got multiple values that will give me um, multiple paths. Now, I am able to choose theta so that I can get on the same path, but not all the time. Okay, I have some variations to that. All right. Any questions? Okay, so that is it for that section. Now, I'm not going to start into the partial derivative section yet. I'm going to wait till Thursday to start that. I've got all homework. See, I've got the homework for the functions with several variables done, and the limits and continuity of higher dimensions done. So those two sections will be the things that you'll be working in homework. So the functions of multiple variables and the limits. Okay, so those two things are going to be for homework for you to practice. Quiz 6 is going to be available. It's due Thursday. Until's having a mind of its own itself. So quiz 6 is due Thursday. All right. And as I stated before, the midterm is coming up soon. So just keep that in mind that it will be coming up soon. Okay. All right. Any questions? And I haven't forgot about homework 5. Quiz 5. I will be getting that graded and back to you. Are there any questions? Okay. All right. Well, that is it for today. You guys have a great rest of the day, and I'll see you on Thursday.
You are currently the only person in this conference.